Okay, today and tomorrow we are going to be doing phase changes. Here is a really rough diagram of the three states of matter: solid, liquid, and gas, and the phase changes that each of them can experience. So if we go from liquid to gas, that's called vaporization. Gas to liquid is condensation. Solid to liquid is known as melting, and liquid to solid is known as freezing. Another word for freezing can be solidification. And then here's a new one for some of you: solid to gas and gas to solid. This is how you make dry ice. Dry ice is made of carbon dioxide. You go straight from the gas stage to the solid stage. You completely skip liquid. From gas to solid is deposition. From solid to gas is sublimation. So there's two factors that actually influence phase change. It's temperature and it's pressure. And a few numbers that I want you all to know is just for basic water. And don't confuse that water is all liquids, but just for water, at 1 atmosphere of pressure, water will freeze at 0 degrees Celsius or 32 degrees Fahrenheit, same thing. And it will boil, which means vaporize, at 100 degrees Celsius and at 212 Fahrenheit. But something to keep in mind, at Denver, Colorado, the mile-high city, they're a mile up in altitude, water actually boils at around 88 degrees Celsius. So as you go up in altitude, the pressure decreases, which means that the boiling points for various liquids will also decrease. We were just talking about how helium that we put in balloons can go from a gas to a liquid at negative 269 degrees Celsius. That's just a few degrees shy of the ultimate cold temperature called absolute zero. Absolute zero is 0 Kelvin, and you can convert that to Celsius by just subtracting 273.15. So 0 minus 273.15 is negative 273.15. So there is no solid state of helium. For nitrogen, which is used by hospitals to preserve cells and tissue and organs and even viruses for study, to get nitrogen as a gas into a liquid, and you see condensation, you know it's going from gas to liquid. That's at negative 195.79 degrees Celsius. One other thing I want to get to is with the whole COVID vaccine transport. You may have heard that Pfizer has had some issues with shipping their vaccine because it has to be at super cold temperatures. And the way that they keep it really, really cold is they use dry ice to transport the vaccines across the country. So I'm going to look up at what temperature CO2 will go through deposition to become a solid. So right now in this room, it's about 73 degrees Fahrenheit, which is somewhere probably in the neighborhood of upper 20s Celsius. Let's see, in this room, CO2 is a gas. Let's see how cold you would have to get it to actually get dry ice. So let me see here. CO2 temp to dry ice. You have to get it down to negative 109 Fahrenheit. And I can do that math on a calculator. I don't have to go to Google and convert. So to figure this out, for Celsius, you're going to do the temperature in Fahrenheit minus 32 divided by 1.8. Pretty sure about that. So let's see. Negative 109 minus 32 divided by 1.8. That's going to be negative 78 degrees Celsius. That's how cold they had to keep the vaccines for Pfizer. Other companies like Moderna and Johnson & Johnson, I don't think have to have their vaccines at super cold temperatures like that. They could just refrigerate it, just like you do in your house with your milk. But in order to transport the vaccines from point A to point B across the country in airplanes, they had to have dry ice. So there was a big shortage of CO2 and dry ice because it was all being used to ship vaccines all across the country. Okay. So I want to show you guys something real quick, just to kind of give you an idea, a little pop culture reference here. Have any of you ever seen the movie Terminator 2? Okay. If you haven't, in the movie Terminator 2, there's a good robot and a bad robot, and they're trying to, one is trying to kill the child version of the savior of the future, and the other robot is trying to protect the child version of the savior of the future. Well, there's a scene in the film where the bad robot gets doused in liquid nitrogen, and he gets all frozen. So I just want to show that to you. And it also shows you another element which you may not have been aware of, but I'll show you that as well. So let's see. I can fix this real quick. No worries, we got this. What? There we go. Terminator 2, liquid nitrogen. Can you hit the light, Emma?
Tampa General is the only hospital named #1 in Tampa Bay 5 years in a row, and named one of America's best hospitals by U.S. News and World Report. Tampa General Hospital. Other hospitals practice medicine. We define it.
So the Vap robot is made out of liquid metal. And that truck is carrying liquid nitrogen. Very cold. So that liquid is all the stuff that makes up the majority of our atmosphere. And when it's warm like this, it's a gas. But in order to condense it into a liquid, you have to get it really, really cold. About what we just looked up, about a negative 109 degrees Celsius. So anything that touches it is going to freeze.
Get the hell out of here! Get out of here! Let's go! Hasta la vista, baby.
That's mercury.
We don't have much time.
Scary. Scary stuff. All right. But that was 2 chemistry examples in one. You had the liquid nitrogen freezing, and then you had the mercury, which froze and then became liquid again, so melted. Mercury is liquid at room temp. They actually use mercury as that movie effect for the liquid robot. All right. Let's keep going. So the first thing I'm going to tell you guys is be sure that you understand the differences in those 6 phase changes. If I were to come up to Jade in the cafeteria, Jade, freezing, what's it from what to what? That's right. Emma, condensation. Okay. It seems kind of rudimentary and a little easy, but you know, you'd be a little surprised. Some people get kind of sort of tongue-tied. So just practice that as we get closer to your. All right, let's continue. Hold on, why is it not working? Okay, and we're back. So let's get to phases that require energy, or phase changes that require energy. Now, on your vocab quiz, you guys had some extra credit questions. And one of those extra credit questions was distinguish between the terms endothermic and ectothermic. Energy, or reactions that require energy, this means an input of energy. Key part of that is in. What prefix means in? Endo or ecto? Endo, like you guys have an endoskeleton. It's inside. So the phase changes that require an input of energy are going to be melting, which is solid to liquid, vaporization, which is liquid to gas, and sublimation, which is solid to gas. These 3 are energy input processes. These 3 are endothermic. Endo means within, and therm means heat. Another word for heat is energy. So let's talk about energy transfer. And to have you grasp this, a lot of us like to have a glass of water with ice. Yes, Carson?
What's an example of sublimation?
Dry ice becoming carbon dioxide again. Okay, let's say if you have a glass of water. You have some ice cubes in there. Now, I need you to tell me what objects or what states or whatevers are cooler or warmer than the others. So let's look at the liquid water. And ice is solid water. Which one of these is the warmer substance? The liquid or the solid? The liquid. So this is going to be the warmer substance. Heat always transfers from hotter object to colder object. It's like diffusion. In diffusion, you want to have a high concentration go down to a lower concentration. Well, the same thing applies to temperature. You want to have the hot transfer down to the cool. So heat transfers from hot to cold. So which way is heat going to be transferred? From the water to the ice or from the ice to the water? All right, so heat is going to be transferred from the ice to the water. So what I want you to tell me is, what is the ice experiencing? Is ice experiencing a heat input or a heat output? Input. Water or ice is experiencing an endothermic reaction. This means that it is basically receiving heat. Now, look at the water's perspective. The liquid water. Is the liquid water gaining heat or is the liquid water losing heat? It's losing heat. This is an ectothermic reaction. Did I say exo? Yeah, well, I meant, that's correct. It's ecto. Exothermic is going to be something different. When it comes to energy, we say ecto. So this is an ectothermic reaction. Heat is lost. It can be. Ecto and exo can be interchangeable, but we use ecto when it comes to temperature change.
Okay, so it'd be exothermic reaction, but ectothermic to the water.
Right. Now, Jade, if you ask your mom for $20, you just became $20 richer. What happened to your mom? What's the opposite of rich? Your mom just became $20 poorer. You have to look at this from both perspectives when you're doing phase change. Heat cannot be created or destroyed. Heat flows and heat cycles. So if you were to hold an ice cube in your hand, it's going to feel cold to you. But you guys are mammals. You're warm-blooded. You have a lot of body heat. Heat is going to flow from your hand to the ice, which means that you are experiencing an ectothermic reaction. You're losing heat. The ice is receiving that heat. And so it's going to melt in your hand because it's getting warmer. It is experiencing an endothermic reaction. It is absorbing that heat. So you have to look at it from both perspectives, the winning side, so to speak, and the losing side. It goes both ways. All right. So when it comes to phase changes that lose heat, these are going to be ectothermic. Well, we have freezing, which is liquid to solid. You're getting colder. We have condensation, which is, gas to liquid. And lastly, we have deposition, which is gas to solid. An example of going from gas to solid is making dry ice from carbon dioxide. It completely skips the liquid phase. Now, the one I want to focus on, I want to talk about vaporization, because I think Tim said evaporation instead of vaporization. You need to know the difference between the two of those. So let's go to the phase change known as vaporization. And we're going to get into what is the difference between vaporization and evaporation. There is a difference. So vaporization is going from a liquid to a gas, and it is an endothermic process, which means it's when you heat up a liquid, it can boil and vaporize into a gas. Now, when water or liquid or mercury or whatever is, liquid nitrogen, liquid helium, whenever it's vaporized, boiling point is reached. And boiling point is the temperature at which a given liquid is converted to a gas. So when it comes to evaporation, I don't care if it's a day in July or a day in January. If there's a puddle outside, in maybe less than a day, the puddle is gone. That puddle is not boiling. It's not going to be 212 degrees Fahrenheit outside to make a puddle boil. Every now and then I have to add water to the turtle pond because water has evaporated from the pond. But the pond is not boiling, or else we'd have turtle soup down there. It's just the top layers of the water. So this is just vaporization that occurs at the surface. If you vaporize the surface, then you have a new surface, and then that will evaporate, then the new surface will evaporate until the entire little puddle is gone. The energy that is being absorbed by the sun is able to eventually break the hydrogen bonds on just the top layer. And when those hydrogen bonds are broken, they're able to evaporate.
So like only the top layer is kind of getting hot enough to boil.
It's getting hot enough not to boil, but for the bonds to break. The bonds have absorbed so much solar energy that they can't, they're getting degraded by the radiation, and they're also getting degraded by the heat caused from the radiation, and they just break. Yeah. It's unique to anything that has hydrogen bonds. Yeah, like helium wouldn't evaporate, you know. Okay, now let's talk about vaporization in a closed container versus an open container and something called vapor pressure. So if I have a closed container, I'm going to draw this for you. So this is a big plug. And I have a jar. And I have this jar on a burner. And this burner is like the burner on a stove, and it's getting really hot. Well, let's just say I have water in here. What is the hottest area of this water? The top layers or the bottom layers? The bottom, because that's where the heat source is. This is the heat source. Now, if you've ever seen water boil, you're going to start to see some bubbles come to the top. What are those bubbles? That's water vapor. And what is lighter? Water vapor or liquid water? That is why water vapor rises and it's starting to boil. But what happens to the water vapor as soon as it starts to get away from the burner? Is it cooling off, or is it maintaining its temperature? It's starting to cool off, which is why some of these water vapor bubbles don't make it to the surface, because they're cooling down as soon as they get away from the burner. So what you have to do is you have something called a convection current, where heat is going to start to cycle. It's going to rise up. I'm going to zoom in on this. It's going to rise up. It's going to cool down. And what does cool air and cool temperatures and cool water do? It sinks. And so it goes back down and it gets heated up again. And then it goes faster and faster and faster. And so hotter air is able to get to the top faster and faster and faster. And sometimes it eventually gets so fast, it's able to maintain its really hot temperature at the very top layer of the water, the surface, and escape as a gas. And that is when you're starting to build up some vapor. So these little wavy lines represent vapor. But I have a container that is closed. So over time, this liquid water is starting to vaporize into a gas. Where can this water vapor go? Nowhere. And so what is happening to the pressure inside of this container? The pressure is building. So because the container is closed, vapor cannot escape. And remember that warm air rises. This increases what we call vapor pressure. Vapor pressure is the pressure generated from liquids vaporizing into a gas and exerting their force against the walls of a container. This is how some steam engines actually work. They convert liquid water to steam, and the pressure of the steam pushes an engine, or this is how a nuclear power plant works, like in Chernobyl, or here, 70 miles up the road in Crystal River. You have the nuclear core reactor, and it heats up water. What does that liquid water get turned into? Steam. And the steam is going to spin a turbine because the steam is rushing through that turbine because it has high pressure. And that turbine is spinning and spinning and spinning. What does the spinning turbine generate? Electricity. And that electricity is distributed to all the neighborhoods and towns and all the stuff in the area. If you have a core that doesn't have electricity, a core that doesn't have liquid water, then you're not going to be able to generate electricity because there's going to be nothing to actually spin the turbine. But that's the whole premise of a nuclear power plant. You just have a nuclear core reactor, which is incredibly hot, and it boils water into a gas, and the gas spins a turbine, which generates electricity. No pollution. Now, as you guys saw in Chernobyl, what happens when the core doesn't have any more water? There's nothing to slow down the heat and control the heat, so the heat just starts to build up, and you have a meltdown. And like literally, the core melts down into the ground. Now, let's do an open container over here. It's going to be a lot different. So you have that convection current, and water is starting to really get hot, and it's circulating throughout the entire container, and you're starting to form steam, which is also called vapor. Can the vapor escape because the container is closed? Sure. So in an open container, did I say closed? I meant open, sorry. In an open container, vapor escapes. So how would you describe the vapor pressure? There is no vapor pressure. It escapes. That's what happened again in Chernobyl. The steam had nowhere to go. So it just went, all the water instantly vaporized, and the steam had to get out, had to go somewhere, so it just ruptured the tank, and everything blew up. Okay. All right, a few more. Let's talk about sublimation and deposition. So let's see if you guys might be able to figure out the word. When something goes through condensation, it condensates. When something goes through vaporization, it vaporizes. When something goes through freezing, it freezes. When something goes through melting and melts. What do you call it when something goes through sublimation? It does what? It sublimates. How about deposition? Yeah, sublimates or sublime, and then deposits. So sublimation is when a solid directly becomes a gas. No liquid. You skip the liquid phase. So we would say that solid CO2, which we call dry ice, sublimes. You can also say sublimates, but sublimes is better, at room temp. So if you had a brick of dry ice in this room, you would start to see the gas just coming off of it because it's subliming. It's not even going to be a liquid. It's just going to go straight from solid to gas. All right. I think that's nearly it. I think all of it's pretty self-explanatory. Yeah, that's about it. Yes, Brennan.
Can you go back to the open container?
The what?
Open container.
Yes, Carson.
Like ice, doesn't it give off? Doesn't ice sublime like solid water? Because like you can see like us, it's like vapor come off of ice. But it
It's
also melts at the same time.
it's actually that's heat that it's absorbing. That's the heat that's going into it, not coming off of it.
If you put ice in a really, really hot place, would it become a liquid and then gas, or would it just go straight to gas?
You could have super hot temperatures. It's all going to also depend on the pressure. Okay, pressure. If you have some, let me put it out this way, Sean. It would become a liquid, but it would likely vaporize so fast you would blink of an eye, it's gone. But technically, it does go from solid to liquid to gas.
It would melt and
It would melt first and then vaporize, but it would be like in a flash. Yeah. Yeah. All right, we're going to stop here.